Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So our next speaker is Professor Ed Lazowska he's the Bill and Melinda Gates Chair in the Computer Science and Engineering Department at University of Washington. Under his stewardship, the department actually became the world's one of the first and foremost research institutions in the US and in the world. But in his technical lives, one of the things that that he worked on a long time ago is, again, in your hands right now. So imagine the 40 years of computer evolution that has happened and how the systems have changed from vacuum tubes to mainframes and so on. And the one thing that has enabled us to scale to these sort of devices that we now have in our hands is the fact that these operating systems, these kernels, have been able to manage the orders of magnitudes of new resources that are available. And some of the algorithms that Professor Lazowska and his students and his collaborators have designed are fundamentally part of each and every operating system, from Windows, from Linux to iOS, to even things on your watches and everything. And so with that, let me welcome Professor Lazowska to the stage.
Well, thank you very much. It's great to be here. You've already been sitting here a long time. Why doesn't everyone stand up for 15 seconds and then sit down, okay? Just stretch. Great, good, thanks. So I asked Chandu what I should speak about and gave him several possibilities. And he asked me to talk about the burgeoning enrollments in computer science in the United States. And I've searched my brain to imagine why he thought that might be of interest to any of you. Let me try to couch it in this way. Interest in computer science in the United States is increasing dramatically now, and that's a good thing. But there is, and I'll talk about why, and I'll show you some of these trends. But there's still an enormous gap between the things that need to be done and the number of jobs that are available and the number of people that we in the United States will ever graduate. You live in a country where the smartest young men and the smartest young women want to be engineers and computer scientists, okay? We live in a country in the United States where the fastest growing undergraduate major is parks, recreation, and leisure, all right? So kids who grow up in the US want to work in, the cruise ship industry or something like this, right? So there's going to continue to be an enormous gap between jobs available in the US, in India, in the world, and the number of people who are educated to take advantage of those jobs. And so this opportunity is going to be enormous for the foreseeable future, and I really think this gap is going to grow. So what I want you to take away from what I have to say is less that there are many, many, many more students in the United States interested in computer science than was the case a few years ago, and rather that the gap between the work to be done and the people available to do it is going to continue to grow, and this is just the greatest field in the world for you. So that's really what I'd like you to take away. So again, I'll talk about trends in student demand in the US. I'll talk about some reasons that I believe that this is going to persist rather than just be another one of the cycles we experience all the time. I'll talk a bit about responding to the demand. And I want to thank Eric Roberts from Stanford and Jim Carrozza from the University of Massachusetts and the National Science Foundation who've helped me gather this material. So let me quickly show you what's going on at my institution in Seattle, Washington, the University of Washington. And with all of the data that I show you, I want to ask you to focus on the slope of the line rather than the numbers, because to you here in Bangalore and in India, the numbers will not seem that great. The important thing is the change in the numbers that's taking place. So, and you may not be able to read the legends on these, but I'll describe them to you. This is incoming students at the University of Washington and their intended major among engineering fields, okay? And it covers about a 7-year period. And what you see is that the interest among entering students in computer science is skyrocketing compared to any other field of engineering. And that was not traditionally the case. We were sort of in the muddle with everybody at constant interest. So what's happening now is interest in various engineering fields is increasing slightly, but interest in computer science is going through the roof. This is interest in our introductory course. Again, just take a look at the slope of the line, not at the absolute number, although these are pretty big numbers for an American university. The blue line is our first introductory course, that's CS1, and the red line is our second introductory course, that's CS2, and these are annual enrollments. So what you see is that 1 year looking backwards, we taught 3,000 students in our CS1 course, but importantly, that's more than double what we were teaching 10 years ago, right? And same in CS2. So that's the University of Washington picture, and that's what interested me in looking at national data. So first of all, across the country, introductory course enrollments are really increasing enormously. This is an article from the New York Times a year ago about the introductory course at Harvard. The enrollment is shown in the chart on the right. It leveled off briefly. It's actually up again this fall, I understand. Here's the interesting thing at Harvard. Students at Harvard want to become successful typically in traditional business, with the exception of Mark Zuckerberg and Bill Gates, all right? So for decades, the largest introductory course at Harvard has been the introductory economics course, the sort of traditional business economics course. And this year, Computer Science 50, the introductory computer science course, is the largest introductory course at Harvard. So more students are taking intro computer science at Harvard than intro economics or any other course, and that's quite a change. But this is not just happening at Harvard, it's happening at Stanford and the University of Pennsylvania and at MIT, right? And it's not just happening at elite private institutions, it's happening at the University of Washington and the University of Michigan and UC Berkeley. At all of these schools, interest in the introductory course is climbing enormously, and it's putting a strain on us in terms of our ability to handle these students. The enrollments are exceeding previous highs. I'll show you the cyclic trends in a minute, but in the United States, we had relatively a surge in enrollment around 1999 or 2000, and then we had a decrease in interest, but interest now is greater than it's ever been in the past by a long distance. A greater proportion of students are taking the second course. So this shows at my school, the University of Washington, the proportion of students who take the first course and continue on to the second course, which is up from about half to 2/3 in just the past few years, right? So people are continuing in the field. At least in some instances, the participation of women is increasing. I see a number of women in the audience here, and I'll come back to this theme in a minute. But this is the percentage of women in our first course, our CS1 course. And again, in 14 years, it's gone from 22% to about 36%. Still not great, but a greater interest in women in the field. In the early days of computing, if you look at photographs of the programmers on ENIAC, you see an amazingly diverse group of people. And that ceased to be the case in the US 10 years ago, 15 years ago, and we're making some progress headed backwards. Now, that was introductory courses. Demand for the major is also increasing. At Stanford, there are now more computer science majors than all of the humanities combined. That's not unusual for India. India has tremendous enrollments in engineering. It is unusual in the United States. Same at MIT, same at the University of Pennsylvania, same at Harvard. So tremendous increases in students in the major. This is the top 25 majors at Harvard about 7 years ago. You see economics, government, social studies, psychology. Computer science is 5th from the bottom. This is the top 25 concentrations at Harvard last year, right? So the only one that has changed significantly is computer science, which has gone from somewhere in the 20s to number 5 among popular majors at Harvard. Again, the numbers are still small. Harvard is a small school compared to most schools in the US or here, but nonetheless, interest is increasing. Carnegie Mellon, Many of the people at Microsoft were originally at Carnegie Mellon, including Jeanette Wing, who you'll hear from later, and of course Raj Reddy. Carnegie Mellon has a very small elite undergraduate program that only takes about 150 students a year. And last year they had more than 6,000 applicants for those 100 positions, right? So just an enormous interest. Another thing that's increasing in the US is demand for upper division courses by non-majors. And again, I'll explain the reasons for all of these things in a few minutes, or attempt to explain them. But the chart on the left shows non-major demand for the third course at Harvey Mudd College, an undergraduate engineering school. On the right is upper division undergraduate enrollments at UC Berkeley, a big, great public university, by students who are not in computer science. So what you see is more and more students who are not computer science majors are taking upper division courses. Class sizes are expanding. Again, the numbers may not be so impressive, so look at the I don't have trends here, but typically upper division courses at smaller schools like Harvard and Cornell were 50 or 60 students, and they're now in the hundreds. Andrew Ng, a widely known faculty member at Stanford, taught a graduate machine learning course last year that had 760 students in it. Again, that may not seem like a lot to you, but this is a course that you would expect to have 50 or 100 students in it. Stanford certainly does not have 760 undergraduate or graduate computer science majors, so people are flocking to computer science to learn what they need to know for other fields, and that's the point I'll come to in a second. So there have always been these cycles in demand. What this graph shows is bachelor's degrees granted in computer science in the US over many, many years. So you can't read this, but on the left is 1966. That's when we first started granting undergraduate degrees. The first peak was in the middle 1980s, right? And then we suffered a decline in interest. The second peak was around the year 2000 or 2001, and we suffered another decline in interest. And interest is now increasing again. So again, the numbers are less important than the trends. This is a field which has cycles of demand. But I actually believe that it's different this time, and I'll cite several reasons, and then hopefully this is something we can discuss during the question and answer period. First, Jeanette Wing has been an advocate for many years of what she calls computational thinking. And I believe that students are finally figuring out that in the 21st century, everybody needs to have facility with computational thinking. Computational thinking maybe isn't even computer programming. It's the way we think in computer science. We think algorithmically. We think logically. We know how to decompose problems into pieces that can be solved independently, and we know how to combine those independent solutions back together into a solution to the overall problem. We know how to debug. Debugging is stepwise fault isolation. We understand models and modeling and former models. We understand grammars, right? So there are a set of things that constitute computational thinking that everybody needs to know. And I think of programming not just as a valuable skill, but as the hands-on, inquiry-based way that we teach computational thinking. And I think students are honestly figuring this out and understanding that they need to take at least an introductory programming course, not just to become a computer programmer, not to go work at a great company like Microsoft, although that's a possible outcome, but rather because programming is the way we learn computational thinking, and everybody needs to know that, even if they're going to be a lawyer or a doctor or something like that. Okay? Secondly, every field is becoming an information field, right? Linguistics is becoming an information field. Biology is becoming an information field. Back in the 1950s, Watson and Crick discovered the biochemistry of DNA, the ACGT double helix business, okay? And what they really discovered was that your DNA is a digital code, and that digital code can be deciphered and modified and rewritten, okay? And from that day forward, the leading edge of biology was in information science. And the ability not just to think computationally, but to actually compute was important. Let me give you another example from when I was an undergraduate many years ago. It shows how long this has been going on. I took a graduate linguistics course with a friend. We were both computer science majors. And historically, in the United States, the main criterion for becoming a graduate student in linguistics had been you spoke a couple of languages, right? And at that point, though, when I was taking this course, linguistics, through work by people like Chomsky and Haj-Ross, was becoming a computational science. People were dealing with formal grammars, okay, and computing against, for that day, large bodies of text, right? And a couple of computer science sophomores, second-year students in computer science, could run circles around graduate students in linguistics who couldn't compute and couldn't think computationally, right? So this is happening to every field, and if you can bend the computer to your will, cause it to do what you want it to do, you're going to have an advantage in almost any field. The third thing is, I think, the reputation of the software industry as a place to work is a lot better than it used to be. And not just the reputation, but the reality. We have this cartoon in the United States called Dilbert. Dilbert is this poor, boring guy who works at a poor, boring technical job and has bosses he hates. And I think this Dilbert reputation of computer science, that you sit in a cubicle and work in a solitary way staring at your screen all day, has really both the stereotype and the reality have disappeared, right? This is a field where even our students who work at hardcore infrastructure jobs at Microsoft and Amazon and Google, all of which have large installations in the Seattle area, claim that they only spend 1/3 of their time actually writing code. The rest is working with teams and with customers in design, right? So the field really is not an insular, isolating field. It's a field in which your ability to work with others and communicate with others is of tremendous and increasing importance. Here's the job situation. I want to spend a bit more time on this. All of the jobs in STEM fields are in computer science, to first approximation. So what's STEM? In the US, we talk about science, technology, engineering, and mathematics. And you hear people talk about the value of a STEM education and STEM jobs and the need for more students in STEM. And that's, in fact, I mean, there's lots of value to studying any field of science, to studying physics or chemistry or applied math or computer science. But the fact is, where the jobs are in STEM and where the job gaps are is in computer science. So every year in the US, the Bureau of Labor Statistics, every 2 years, projects job openings going forward a decade. And they only do this every other year, and they lag by a year. So the newest projections that are available are for 2012 through 2022. And what I've charted here are all of their predictions for newly created jobs in the decade 2012 to 2022 for the various STEM fields. So these are jobs that will be newly created in the US in this decade. And what you see is that 71% of them are in computer science, right? So that's the blue part of the oval, the circle. The red part, right, 15% is newly created jobs in all other engineering fields. So that's electrical, mechanical, civil, chemical, aeronautical, industrial, right? All added together is 15% of new jobs, whereas the computing occupations are 71% of newly created jobs in this decade in the US. All of the physical sciences are 3 or 4%. All of the life sciences are 3 or 4%. All of the mathematical sciences are 3 or 4%. All of the social sciences are 3 or 4%. In the United States, where are all the degrees? All of the degrees in the US are in the social sciences, right? People majoring in psychology or sociology for some reason, certainly unrelated to job opportunities. Now, these are newly created jobs. We can also consider all available jobs, whether they're newly created or whether they're available to retirements, due to retirements. And computer science is a smaller percentage here because we're a younger field and we're retiring less rapidly than other fields. But even if you look at all available jobs in this decade in STEM fields, computer science is 57% of all available jobs. Engineering has now grown to 25%. If you look at computer science and engineering added together, they're 80 or 85% in both of these. Okay? So once again, the physical sciences, the life sciences, the mathematical sciences, and the social sciences combined contribute only 15 or 20%. Okay? So all of the available jobs are in computer science or in other fields of engineering. So there's just a tremendous opportunity in terms of newly created jobs and available jobs in the field that you are studying. Here's the situation in Washington State. Again, this is just one place in the United States, but it's where I happen to live, and it's also where there's a really robust software industry. Washington State is, of course, the home of Microsoft. It's the home of Amazon. It has substantial installations, engineering offices of all of the major companies from elsewhere in the country. Facebook, Google, Twitter, LinkedIn, Alibaba now are all present in the Seattle area. And there was a study done a year ago that looked at the gap between jobs available and degrees granted in Seattle across all fields. And what this study found was there were only 4 fields in which there was any gap at all in the state between jobs available and degrees granted, and only 2 of those fields had a gap at the bachelor's level. Those were computer science and, secondly, all the rest of engineering added together. In this chart, the gray left-hand part of each bar is the degrees granted in the state each year, okay? And the blue bar, the blue portion of the bar, is additional available jobs. So the total length of the bar is jobs available per year in the state. Now, these are predictions, measurements. They're not gospel. They're not precisely accurate, but they're the best we've got. And what you see is in the state of Washington, at the bachelor's level, there are only 2 fields that have a gap between jobs available and degrees granted. One of them is computer science. The other one is all of the 8 fields of engineering added together. And the gap in computer science is 2.5 times as large as the gap in engineering, right? So across the United States and in the state of Washington and around the world, the opportunities in computer science are absolutely enormous. And all of us want to encourage you to pursue this field, whether it is to use computer science skills in some other field, or to use it as a software engineer, or to become a researcher at a company like Microsoft. The opportunities are just extraordinary no matter what you choose. Here's one other factor that causes me to believe that this interest in the field will persist, although there are always going to be some cycles. There's an organization from Seattle called Code.org. How many of you participated in the Hour of Code or know people who did? Ah, great, right? So Hadi Partovi on the right is a former Microsoft employee, actually twice a Microsoft employee, who 2 years ago decided to take on the challenge of kids not being exposed to computer science in schools in the United States and around the world, in fact. And he created this organization called Code.org, and last December and this December ran something called the Hour of Code. And his goal, right, was that every child would spend just 1 hour learning to program in a drag-and-drop programming environment. So they're not writing Java or C or C#, but they are learning algorithms and loops and conditionals, debugging, the sorts of things we deal with all the time. And between last year's Hour of Code and this year's Hour of Code, 95 million students have spent 1 hour coding. That's a very big number compared to all of the kids in the world. It's really just extraordinary, right? So this has made a tremendous dent in the field. They are now developing materials to help people teach computer science from elementary school to high school. And I really think this is going to cause a significant change in student interest. By the way, in the first Hour of Code, the first year, about 25 million students participated in the Hour of Code, but it was more women and more minorities than in the entire history, the entire 50-year history of computer science, right? So this has affected a broad cross-section of the population in ways that we haven't reached them before. So I believe that cycles will continue. There will always be ups and downs, but this trend of interest, I honestly believe, is going to continue to grow. And let me talk a little bit about how universities in the US are going to respond, and then I'll conclude and leave the next speaker a bit of extra time. At universities in the US, a relatively small percentage of the faculty are in computer science, but a growing percentage of students are in computer science, and plus there is growing introductory course demand, upper division demand by non-majors, graduate non-major demand. Universities are not going to be able to respond in a way that scales their programs to correspond to this increase in interest. And we really had seen this happen before, and it didn't work out very well. I showed you that in the middle 80s and the middle 2000s, student demand increased. What happened in the US was class sizes grew. We had more and more courses taught by teaching assistants. Instructional quality declined. Faculty left universities for industry jobs. Industry jobs are great, but you need faculty to teach the students. And it's not clear that we're going to do much better this time. There are a set of possibilities, of course. You can restrict the size of the major. You can exclude non-majors from upper division courses. We can retreat to the core of computer science and leave the rest to somebody else. We can have gigantic classes and decreases in instructional quality. We can hope that it all works online, all right? I want to talk about my concern about diversity, and then I truly will conclude. Let me explain why diversity matters in this field, first of all. Raj said to you that computers are used by people. That's pretty obvious, but each of us has our own perspectives that we bring to any design problem. And I am going to design systems that are best suited for use by 60-year-old white North American males, because that's what I am, right? So if you have systems that are designed by only one part of the population, then those systems are unlikely to meet the needs of the whole population, right? Design of computer systems is inherently really creative. This is something our colleague Bill Wolf has made very clear. It's a creative process, and everybody brings their own perspective to a creative process. And if you don't have the full diversity of the population represented, then you're going to get a worse solution. So the reason for wanting a diverse workforce in computing is partly, well, you'll have more workers, and partly it's more fair. But I think the most important reason is you get a better outcome at the end if you have a more diverse population contributing. Now, here's my concern. In the US, most academic programs in computer science or any other field want to have reasonably sized upper division classes, and we may not have controls over who takes those classes. So the way we limit the size of the upper division student population is by having a hostile introductory course. We call them a weed out course, okay? An introductory course, the goal of which is to get you not to continue, to choose some other major, to show that you're good enough, right? And so let me show you some statistics from the University of Washington. We do not do very well in diversity in our undergrad population. We do better than others. This is computer science degrees at the University of Washington, which have grown from about 16% to about 30% women in the past 5 or 6 years. This is the list of all computer science departments, percent female in the US, and this is undergraduate programs at graduate departments. So you see that the undergraduate programs at departments in the US that have graduate programs have just a terrible representation of women, right? Now, here's the interesting statistic. Whenever a student takes our first course at the University of Washington, we ask them to fill out a survey, okay? And one of the questions on that survey says, what's your interest in becoming a computer science major? On a scale from 1 to 5. 1 is, I have no interest at all. 3 is, I don't know, I haven't really thought about one way or the other. And 5 is, yes, I want to be a computer science major, right? And then, a year later, when students choose a major, right, we go back and look at what box they checked, right? What did they say when they took the first introductory course? And nearly 60% of the women who become our majors did not have that intention when they took the introductory course. right? So they either didn't have prior exposure or they had negative prior exposure, and they took a welcoming introductory course, a course that really tries to help everybody succeed, and they discovered they enjoyed computer science and they were good at it, and they chose the major. And that's true of only about 36% of the men, right? So women, much more than men, discover computer science through a welcoming introductory course and succeed at it. So if you create a hostile introductory course to control interest in your major because you don't have enough faculty to handle all the students, the people you're going to deselect, the people you're going to drive away from the field, are going to be predominantly the people who are already underrepresented. So I have this serious fear that the underrepresentation of women and minorities, the underrepresentation of diversity in computer science is going to become worse in the next 5 or 10 years because we're going to face these expanding enrollments and we're going to try to deal with it by having weed out introductory courses that get rid of people. And that's going to be terrible for the field, terrible for the solutions we produce. We're going to have more and more solutions that Raj will be able to give talks making fun of. And that's not going to be good for any of us. Finally, and I really will conclude here, this is my view of the field of computer science. And this has been unpopular with some of my colleagues, but I think they're finally coming around. In the middle is what I'll call core computer science. This is compilers and operating systems and programming languages and networks and database systems. It's all the things that we've been doing for 50 years. It's where I've spent almost my entire career, right? And this core of computer science is still extremely important, and we're still making advances, and those advances are really necessary. But around the outside, the colored labels, those are the things that really affect people's lives, right? The speed of a microprocessor, the amount of memory on your computer, the precise internal organization of your operating system, that's not something that makes a sort of direct impact on how happy you are, maybe an indirect impact. What matters to you is whether you have efficient transportation, whether you have cost-effective and sustainable energy, whether you have decent health care, whether you have decent education, right? Those are the things that matter to people. And what I want to argue is that advances in computer science are essential to all of those societal grand challenges. And what's been happening in recent years is advances in the core of the field, advances in systems and architecture and networking, are being coupled to these grand challenges by a set of newer fields, okay? By things such as machine learning, human-computer interaction, computer vision, robotics, mobile computing, big data, and the cloud, right? So I think we're in a position now where if what you care about is changing the world in ways that affect people's lives, these are these labels around the outside, where you want to be is in computer science, because the future of healthcare, the future of transportation, the future of energy, of education, the future of scientific discovery, the future of all of these things depends on the future of our field. Okay? And what we have to do is embrace all of these things as part of what we do. All right? That is, the future of computer science is not just better operating systems or better compilers or better programming languages. The future of computer science is tackling all of these grand challenges in partnership with others, playing a role in making the world a better place. And that's what I think we're going to be able to do together. I have many more slides that talk about how universities in the US are approaching these issues of student interest, but I don't expect that's going to be of interest to you. So I'm going to leave you with this view of computer science as a field and turn this over to the panel. Thank you very much for your attention.